So is my screen visible to all of you? So is my screen visible to all of you?
Yes, ma'am, visible.
Okay, thank you.
Yes, ma'am.
Okay, so good afternoon all of you. Today we are going to discuss about the topic Introductory Organic Chemistry Part 2, which is an NPTEL platform course. And the course instructors are Professor Harinath Chakrapani and Professor Neeraja Dashaputri from ICE Pune. And I am Simran, your PMRF teaching assistant. So today we are going to discuss about week 4, that is reactions of carboxylic acids and its derivatives. So previously we have taken 3 lectures. So I hope all of you have understood all the videos which I have already uploaded on the YouTube channel. So if anyone has any doubt regarding these 3 weeks, so please let me know now. Anyone has any doubt regarding the previous lecture, or should I move forward with this? Okay. If no one has any query, then I'm moving forward towards the reactions of carboxylic acids and its derivatives. So coming to problem number 1. So in problem number 1, they are asking which of the following acids has the smallest dissociation constant. So what do you mean by dissociation constant? First of all, you need to know the dissociation constant of an acid. So, guys, dissociation constant is nothing but how acid dissociates in water to get you proton and the conjugate base. So, the amount of proton, the amount of H plus, which the acid release on dissociation, the concentration of H plus, if it is high, then we say that the dissociation of acid is high. So, dissociation of acid directly depends on the concentration of the hydrogen ion which it releases, which it dissociates in water. So, here we will say that this H plus, the acid, the tendency of an acid to release this H plus is known as the dissociation constant. So, here we have 4 options and you have to find out the smallest dissociation constant. What do you mean by smallest dissociation constant? Now here the concentration of H plus will get lower. So here you will say that yes, the Ka, the dissociation constant of acid is lower and the concentration of H plus in the medium is also low. So that means a poor acid, a weak acid, will give you a small dissociation constant, while a strong acid will dissociate this H plus higher and leads to the concentration of H plus in the medium high. So having the high dissociation constant. So weak acid has low dissociation constant and strong acid has higher dissociation constant. So now you have to figure it out among these 4 which is having the smallest dissociation constant. So can anyone tell me based on these 4 which could have a smallest dissociation constant? Which acid?
Option 3.
Okay. Any other answer than option 3? Okay. So, guys, what is happening here? Now you have to find out the acidity of these acids. So, now coming to this first, here fluorine is getting attached at the alpha position of the acid. So, here the the negative charge which is going to accumulate on this carboxylate will be stabilized by the inductive effect, that is the minus I effect of the fluorine. So fluorine being electronegative atom and it is attached at the alpha position of this carbon, that is why the negative charge of this carboxylate is now stabilized. So it will release this proton very readily, right? So here in the second case, it is attached on the beta position, and we know that inductive effect depends on the distance. So it is distance dependent effect. So here the inductive effect of this fluorine will be lesser than alpha position. So having the fluorine attached at the beta position will stabilize the carboxylate ion, but it doesn't stabilize the carboxylate ion that much which is present in the case of 1. So now coming to option number 3. So here what is happening again, this is attached at the beta position and it is attaching at the alpha position. So bromine is less electronegative than fluorine, but here also alpha beta case is there. So be- bromine at the beta position will be stabilizing this carboxylate ion lesser than the bromine present at the alpha position. So here the stability of this carboxylate will be highest in the case of 1. In the case of 1, the stability of this carboxylate will be highest. So what you mean by now the stability? Here the stability will encounter to the acidity of the acid. Why? Because higher the stability of the carboxylate ion, higher will be the release of H plus. So greater readily it will release the H plus in the medium. So this acid will becomes now the strongest acid in between these four. And which is the weakest acid in these four? Because that will decide the smallest dissociation constant. I have told you that the strong acid has highest dissociation constant and the weak acid has lower dissociation constant. So you have to find out the weakest acid. What you mean by weakest acid? Which will not give you H plus very readily in the medium. The concentration of H plus should be low in the medium. So here we have seen that first is the highest dissociation constant containing acid, and B, if you go through the electronegativity, then bromine will be having a low acidity. So here bromine at the beta position will stabilize this carboxylate ion least. Among these four, the 3 is least stabilized in the terms of carboxylate ion, and that is why it will not give you the H plus very readily in the medium. So here the smallest dissociation constant belongs to this particular molecule. So third acid is the weakest acid and has the smallest dissociation constant. So option number 3 will be the right one. So is it clear to all of you why it is the right one? Any queries?
Yes, sir.
Okay.
Yes, ma'am. Clear.
Okay. So coming to problem number 2. So I have already discussed about the cyanohydrin reactions on ketone. When we are discussing about the carbonyl compounds, we have discussed this reaction. Okay, so they are asking the formation of cyanohydrin from a ketone is an example of electrophilic addition, nucleophilic substitution, and electrophilic substitution. So can anyone quickly tell me which it belongs to? So for convenience, I am giving the mechanism of cyanohydrin formation, which I have already told you guys. That first of all, what will happen? The nucleophile will attack on the carbonyl carbon. Then this tetrahedral complex will form. That is the
Nucleophilic addition.
nucleophilic addition. Okay. Any other answer than nucleophilic addition? Okay, so everyone agrees with nucleophilic addition. Okay. So what is happening in the cyanohydrin formation, guys? First of all, this nucleophile will attack on this carbonyl carbon. Then this alkoxide will form. It will take the proton, and this cyanohydrin is getting formed. So here, what is changing? See, first of all, the nucleophile is adding, and here, rather than the substitution, it is the nucleophilic addition which is taking place, right? See, electrophile is not taking part, so that is why these two option of electrophilic will be cancelled. Now there is a thing between this two option. So now nucleophilic addition and nucleophilic substitution. When you will say the nucleophilic substitution, see, first of all, nucleophile is getting added, that is fine. But now in the second step, there is no leaving group that is leaving out and your nucleophile is getting replaced. So here it is the case of addition rather than the substitution, because leaving group, your nucleophile is not going to replace the leaving group. So here there is no leaving group present and there is a quaternary carbon which is getting formed, cyanohydrin. That is why we are saying that the nucleophile which is behaving here, the cyanide, is adding to the carbon. That is why it is a nucleophilic addition reaction, not the nucleophilic substitution reaction. So is it clear? So then if it is clear, moving to problem number 3. So in the question they are asking, identify the intermediate X and product Y in the following reaction sequence. So you have to identify this X and Y. So first of all, going to first reaction, here your Grignard reagent, that is this methyl magnesium bromide, is reacting with carbon dioxide in presence of ether. So what you will get? So there are pair of X and Y. Four options are there. So you have to figure it out which is X, which is Y. Any answers? Any guesses? What could be the possible answer?
Option A.
Option A. Okay. So how option A? See what is happening here. Your magnesium bromide is having the partial positive charge and it is having a negative charge. So Grignard reagent have a property of having a positive and negative charge. So now CO2 carbonyl carbon is present. So here this CO2 carbon is electrophilic in nature. So it will attack onto this carbonyl in this way, right? So this R will attack onto carbonyl carbon and this intermediate is getting formed. So here what you will form in the case in this case X is what? Methyl is adding on to carbonyl carbon and this oxyanion which is forming here O minus will form a bond with magnesium like this. So here you will get to form CH3, this CH3 attacking onto the carbonyl carbon of CO2. CO2 is getting attached and then the CO minus which is present here. CO minus. So one of the bond will attach with the magnesium bromide to give you this X. So this is common in 1 and 4. So X is this compound. But now they are saying that hydrolysis is also happening in the same. So hydrolysis is the second step. So what will happen now in hydrolysis? OH2, the water molecule will add on. Now this is OH2. So here what will happen? Like this. Now your water molecule will take up this magnesium X, that is magnesium bromide in our case, and will lead you to formation of this acid. So here also this O minus will take up H plus and this OH minus will form a bond with magnesium bromide to give you MgBrOH like this. So here also you will get the hydrolysis product as acid rather than aldehyde. So this will be the option number 1 will be the correct option rather than 4. So is it clear? Okay, so if it is
Yes, ma'am.
okay, then I'm moving to problem number 4. So in problem number 4, you have to predict the final product in the given reaction. So there are two steps in the reaction. First of all, your acid is reacting with silver hydroxide. So can anyone tell me, is silver hydroxide base, acid, what? So silver hydroxide is a base or acid?
Base.
Base. Yeah. So silver hydroxide is a base. So it will be having a OH minus and Ag plus. Right. So now what will happen if you have a acidic proton in the reaction? So what will a base do? First of all, it will give you a acid base reaction, right? So first of all, this base will abstract the acidic proton. So before behaving as a nucleophile, but silver hydroxide is a weak base as well, so it is not going to behave as a nucleophile. But here it will deprotonate this OH and will give you a carboxylate. A benzoate kind of thing is getting formed here. And what will happen next? This oxyanion, which is generated at this position, now in the second step will attack to the carbon and bromine will leave out. Okay, so this is how, first of all, this silver hydroxide will take up one proton from the acid because it is a base. In the second step, the oxygen ion which is getting formed will attack on the will attack on the allyl bromide to give you this Br minus as a leaving group. So now tell me which is the correct answer? Which is the correct option? Option number?
Option C.
Yeah. Option C is the correct.
Option C.
Yeah. Option C is the correct one. Okay, your oxygen ion which is getting formed, this O minus will attack on the carbon and Br will leave out. So here OC bond is getting formed. So that is why you are getting this. Fine. So coming to problem number 5. So here in the problem number 5, again you have to find out the major organic product Q. So basically you have to find out Q. So before that you need to know what is P. So here what is happening? You have a ketone and they are reacting with diazomethane. So here diazomethane reaction is going to take place with ketone in presence of heat. So now how the diazomethane will react? So see guys, this is the general reactivity of diazomethane with different carbonyl and alkyne alkenes. So here I have given a chart so you can go through this. So now in our case we have this aldehyde. Sorry, we have this ketone. So in diazomethane, what will it do? This CH2 has a minus charge, right? So here it will attack to this carbonyl carbon and this O minus is getting formed. So here in our case, this CH2 minus will attack onto this carbonyl carbon and give you a oxygen ion. Now what will happen? As N2 you know is a leaving group, right? N2 is a gas and it behaves as a leaving group as well. So now the oxygen ion will attack on the adjacent carbon to give you the epoxide formation and N2 will leave out. So here epoxide is getting formed. So now if you have a reaction of ketone and diazomethane, then what will happen? The oxygen ion will attack on the adjacent carbon to release the N2 gas, which is the driving force. So here the epoxide ring is getting formed. So now first step is sorted. In P, what will be there? A epoxide ring, right? So now in the second step, as you have to find the Q. So in the second step, they have taken a alcohol in presence of sulfuric acid. So now what will alcohol do? If you have this epoxide in hand, now what will alcohol do? I'm just writing it as ROH. Okay. So alcohol is a nucleophile, so it has to open the epoxide ring. So opening of epoxide ring will take place two ways, either pathway 1 or pathway 2. So now can anyone tell me which pathway is operative here? Which is facile? Pathway 1 or pathway 2? Based on the stability of carbocation, I'm giving you a hint.
Pathway 1.
Pathway 1, right. How pathway 1 guys? See, if you break epoxide ring from here, so there is a positive charge which is getting at this carbon and which is a tertiary carbocation, right? But if you break the bond here, then you will end up having a positive charge at this carbon. So what is this? This is a primary carbocation. So which is more stable? Tertiary carbocation is more stable. So here the bond cleavage will take place from here to give you the positive charge on the tertiary carbocation, and now your nucleophile will attack on this to give you this product CH2OH. Basically you will have a CH2OH over there and this OET, which is coming from this nucleophile, right? And this is how you will get the product. So now tell me which is the correct option. Which is the correct option?
Option B.
Option B, right. So option B will be the correct one. So you will have, first of all, epoxide ring will form, and then this nucleophile will attack on the epoxide ring to get the epoxide ring open to give you this alcohol, right? So is it clear to all of you?
What is the role of sulfuric acid in the second step?
Role of sulfuric acid. Okay. So basically, what will happen? Your epoxide ring is not going to cleave as it is. So you have to activate it. So sulfuric acid being an acid, it will protonate this oxygen, right? To make the epoxide ring opening facile. So you have to add a acid in the medium to make your epoxide ring activated towards the nucleophilic attack. So is it clear the role of sulfuric acid?
Yes, ma'am.
Okay. So coming to problem number 6. So they are saying the relative reactivity of acyl compounds towards nucleophilic substitutions are in order of what? So you have to arrange these acyl compounds towards the nucleophilic substitution order. Okay, so these contain acid chloride, ester, acid anhydride, and amide. So you have to place it according to nucleophilic substitution. So this is the structure of each. So now nucleophilic substitution. What do you mean by nucleophilic substitution? That nucleophile is going to attack on the carbonyl carbon and substitution will take place, means this will leave out. So can anyone tell me what will be the correct order based on these four options?
Option 3.
Any other option than option 3? Okay. So now what is the concept behind it? Here the nucleophile will attack on the carbonyl carbon and this particular R group has to leave out. Right. So it is based on the basically the electrophilicity and also the leaving ability of the leaving group. So if electrophilicity of this carbon is high, nucleophilic addition is very much facile and substitution is depend on the rate of leaving group. So ability of leaving group basically. So here in the case of acid chloride, see one by one we will see. So here in the case of acid anhydride first. So in the case of acid anhydride, this anhydride this oxygen ion is in resonance with this carbonyl carbon, right? So it is in resonance with this carbonyl group. So here because of the resonance, the electrophilicity at this carbon is reduced. Then this acid chloride. So if it is reduced, then coming to acid chloride, here due to the electronegativity of the chlorine, it will make this center highly electrophilic uh, because of uh, because of the electronegativity of this chlorine. It will take the electron towards itself. So the electrophilicity at this carbon is higher, and also Cl will behave as a good leaving group. Cl minus is a good leaving group, and also the electrophilicity at this carbon is higher. Then coming to third, here also there is a delocalization. There is a resonance between this carbonyl group and this amine. So here also this is not that much electrophilic. Here also the conjugation is there. Here also the conjugation is there. But now in this anhydride group, the oxygen lone pairs are divided into two cases. Here the delocalization of this oxygen lone pair is present on both of the carbonyl compounds, right? So but now as you can see, this acid chloride is having the highest rate for the nucleophilic substitution. Why? Because of the higher electrophilicity at this carbon and higher ability of the leaving group to leave out. But when you compare these three resonating structures, now in which the resonance is least, see, in which the electrophilicity at this carbon is higher. We have two carbons in acid and hydride. So at one point, there will be a carbonyl and a delocalized species present in the mixture. So here, the electrophilicity of one of the carbon will remain as it is, but one of the carbon electrophilicity goes down. So here, in the case of anhydride, the electrophilicity of the carbon is higher than amide and ester. Sorry. So that is why we are saying that the acid chloride is having the higher nucleophilic substitution ability than acid anhydride. And in between this ester and amide, can anyone tell me which is having the higher nucleophilic substitution ability? Between this acid and ester. Okay. So I am saying that higher nucleophilic substitution ability. So the electrophilic character is higher in the case of amide or ester of this carbon. You have to figure it out. So here the oxygen and nitrogen, which is more electronegative, oxygen is more electronegative than nitrogen. So that is why the delocalization in the case of amide is higher than ester, which means there is a partial positive charge more present at this center rather than in ester. So that is why we are saying that the electrophilic character of this carbon is higher in the case of ester than amide. So now, coming to the conclusion, it is highest, the nucleophilic substitution ability is highest for acid chloride, then for acid anhydride, then for ester, and then for amide. So now, that is why we are seeing here that acid chloride is higher than acid anhydride, then ester, and then amide. So option number C is the correct one. So is it clear to all of you this much? Anyone has any doubt regarding this question? Is it clear, guys? Should I move forward?
Excuse me, ma'am, how acid anhydride take as compared to ester and amide? Please explain again.
Okay. See, when you see an acid anhydride, the oxygen lone pairs are present in the conjugation with both of these carbonyl compounds, right? But here in the case of ester, as you can see, the oxygen lone pair is solely in the conjugation with this carbonyl compound, with a single carbonyl compound. So there could be a resonance structure if you draw that this will be O minus, this will be oxygen. So this will be a one of the resonating structure of this anhydride, right? But when so here electrophilicity at one of the carbon is compromised, it is reduced, but electrophilicity at this carbon is as it is, right? It is not going to be lower. But when you come in the case of ester, this lone pair has only one carbonyl to donate. So the resonating structure will be like this. Here O minus, this will be O, and this will be double bond. So now if you compare this 1 and 2, which is more electrophilic? the centers. Nucleophile will add on which of the species first? One or two?
Second one.
Yeah. So nucleophile now has another carbonyl here which is present and which has a higher electrophilicity than this particular junction and this particular species. That is why nucleophilic substitution is higher in the case of acid anhydride than ester. And ester, and if you compare ester and amide, you have to think about the electronegativity of oxygen and nitrogen. So the donor ability of oxygen nitrogen, nitrogen has a higher donor ability than oxygen because of the electronegativity. Oxygen is more electronegative than nitrogen. So that is why nitrogen will donate more. It means it will resonate more. It means the electrophilic center will be, now this carbon becomes the less electrophilic than ester group. So is it clear to all of you now?
Yes, ma'am.
Okay. Okay, so I'm moving forward with problem number 7. So in the problem number 7, they are saying predict the products of the following reaction. So now you have to predict the product. What will be this in this reaction? So ethanol, and heat. Again, you have a alcohol as a nucleophile. So can anyone tell me quickly? It is a very simple question. What will be the possible answer of this question?
Option B.
Option B. Okay. Any other answer than option B? Okay. So let me answer it then. You have ethanol, right? So here, as you can see, you have the electrophilic carbonyl carbons, right? So both are symmetrical. So this molecule is symmetrical. So attacking of this nucleophile will takes place either of this carbonyl carbon, right? Doesn't matter on which it will takes place. So if it is attacking on this carbonyl carbon, then what will happen? I'm just writing the core part, 5 member. So this is O minus. This is the carbonyl group as it is, which is untouched. This is oxygen. This will be the ring. Fine. And here you have a methyl group. This is oxygen. This is hydrogen. And now here you have plus charge. So if this proton will go and you will neutralize the charge, sorry, you will neutralize the charge, then now what will happen? Here this oxyanion has to come down. And what will happen now? You have added this nucleophile, so obviously this is not going to leave, right? You have added it, and if you leave this particular group out, then you will come at the starting material only. So here the cleavage of this lactone ring will take place. So this lactone ring will open up, and what you will get here? This O minus after cleavage and this carbonate, right? And this is connected to what? This OET group. So now, being in the acidic medium, that is basically being in the ethanol, so here this O minus will take up the proton from the ethanol, and again you will get a proton here rather than a minus charge. So this will be the particular outcome which you are going to have with this benzene ring attached. Okay, I'm not writing the benzene ring, but it's also attached here. So what will be the now tell me what will be the correct option? Option number 4. Option number 4 will be the correct one. So now, first of all, what will happen here? Aldehyde and CO2 is not going to leave out. What will happen? This alcohol will behave as a nucleophile. It will attack on the carbonyl carbon. As your two carbonyl carbons are are equivalent because of the symmetry in the molecule. So one of the carbonyl compound will get attacked by the nucleophile, and when it come down, the alkoxide ion, then this lectone ring will open up, and the driving force is the opening of the lectone ring to give you this particular compound. So is it understood, all of you? Is it correct, or do you have any query in this? Clear to all of you?
Yes, ma'am.
Okay. Coming to problem number 8. So in the problem number 8, you have to identify the suitable reagent for the following conversion. So what is happening in the conversion? So basically this alkene is going to convert in this epoxide ring. So you have four options, and among these you have to identify the suitable reagent. So any guesses? Which reagent is going to give you the epoxide ring here? Any answers?
Option A.
Option A.
MCPBA.
MCPB. Okay. So option A, all of you are saying. Okay, guys. So let me tell you that MCPBA and H2O2 in NaOH, not in acetic acid. H2O2 in NaOH and MCPBA is going to deliver you the both will deliver you the epoxide ring. So now you have to identify among these two which is the suitable reagent for this. So here you have to look at the electronics of this alkene ring. So here this alkene, is it electron deficient or electron rich? This alkene. Think about it. Is it electron deficient, the alkene, or electron rich in nature?
Electron rich.
Electron rich. Okay. So if you are saying it is electron rich, then you are not considering this carbonyl group as here. So if this carbonyl is not there, then you can say yes, it is somewhat electron rich. But because of the presence of this carbonyl group, what will happen? It is now in the conjugation with this carbonyl. So that is why, which makes this ring electron deficient rather than electron rich, because the electron density is now taken by this carbonyl group basically. So here you are also know that this carbonyl has a electron withdrawing ability, right? So if you have a electron withdrawing group attached at one of the end of the alkene, then you how you can say that it is electron rich? It will withdraw the electrons from this alkene, the carbonyl group, and that is why will make this alkene electron deficient rather than electron rich. And I have to tell you one thing, that MCPBA, that is metachloroperbenzoic acid, will react on, it has a basically selectivity for electron rich alkenes. It will epoxide those alkene having the electron rich carbons, because it is a deficient electron deficient oxygen which is present in MCBBA. So the oxygen will attach on those alkenes having the electron rich behavior. Okay. But when you come to H2O2, here if you have this H2O2 present, now this H2O2 will react with this electron deficient alkene to give you the epoxide ring formation like this. First of all, this H2O2 oxyanion will attack on this alkene of the carbon of the alkene, and then it will resonate to give you this carbonyl carbon. So here again this oxyanion come down, and again this alkene will trap this oxygen to leave you the release of this OH minus to give you the epoxide as a product. But if you add the MCPBA in this reaction, epoxidation will not take place because now your electron density at the alkene is not there. So here, because of the presence of this carbonyl group, it will withdraw the electrons from the alkene, and MCPBA has a selectivity for electron rich alkene rather than the electron deficient. So here H2O2 and NaOH will be operative and suitable reagent, because H2O2 and NaOH will leads the epoxide formation in electron deficient alkene rings. So here MCPBA is not the right answer, but H2O2 and NaOH is the correct one. So is it understood, all of you? Should I have to repeat it? Any queries, any doubts in this question? Why MCPBA is not operative here?
No, ma'am, clear.
Okay. So if it is understood, then coming to problem number 9. So in the problem number 9, they're asking among the following esters, the one that undergoes acid catalyzed hydrolysis fastest. So you have to identify the one ester which will undergo the acid hydrolysis fastest. What do you mean by acid catalyzed hydrolysis? So here what will happen first? Acid catalyzed hydrolysis, this carbonyl carbon will get protonated by the acid, and then this will happen to give you a carbocation at this position. So here this carbonyl carbon will get a positive charge. So in these following esters, so the mechanism of this acid hydrolysis is this basically. Acid first of all protonate the carbonyl carbon, then a carbon will get a positive charge after the resonance, and then the leave then the attack of this water will takes place. So if water will attack, then what will happen? This carbon is getting a OH minus, and here this hydrolysis will takes place. This R1OH is going to leave out. So here oxyanion will, so basically lone pair of this OH will come down, and this will leave out. So just take your time, understand the mechanism, acid catalyzed hydrolysis of ester. So first of all, acid will protonate the carbonyl carbon, generate a carbocation at this carbonyl carbon, then water will attack. If water is going to attack at this position, you will get a OH2, right? So one proton will leave out from the water molecule, and here basically this oxygen lone pair will take up that proton from this water to get you this R1OH positive. This oxygen lone pair come down, and this R1OH, which is a neutral species, now leave out to give you acid. So from ester you have acid. So the basic concept behind the acid catalyzed hydrolysis is you will get a carbocation at this carbonyl carbon. So higher the stability of the carbonyl carbon positive charge, higher will be the rate of acid catalyzed hydrolysis. So now you have to figure it out that if it is a carbonyl compound and you will get a positive charge, you are going to get a positive charge at this carbon. So higher the stability of this positive charge at this carbon, higher will be the fastest switch with the hydrolysis. So now in these four options you have to figure it out which will more stabilize this positive charge. So if you figure it out, the answer is that. So can anyone now tell me what would be the probable answer among these four? Which acid will undergo hydrolysis fastest? Any guesses, guys?
Option D.
Option B. Okay. So guys, what is happening here? I have told you this positive charge is getting formed, right? So this positive charge will stabilized by the resonance and also the plus I effect. If you consider that methyl is going to give you a plus I effect, that is the electron releasing group, and will give you give the stabilization to this carbocation. But here you are missing one thing. What? That this hydroxy being not a electron releasing group, but it will give you a plus R effect. So if it is going to give you the plus R effect, then what will happen? This carbonyl, this will be get oxygen, right? So it is now going to stabilize your positive charge more. Because of the plus R effect, because of the resonance, you will get a stabilization at this positive charge, because now the electron density at this carbon is going to increase. Right? From the ring, the electron density is going to increase at this position. And also in the case of hydroxyl at this position, meta position, here also it is imparting the stability to the positive charge. So I am not saying that methyl is not going to impart the stability to the positive charge, but the extent to which this hydroxy groups are imparting the stabilization to positive charge is higher than methyl group. So this is the least stabilized ester. It will undergo the hydrolysis least. Okay. After that, you will say that this methyl is going to give you the higher acid catalyzed hydrolysis than this particular one group. Now coming to this option number 2 and 3, which is fastest. Can anyone tell me which is the fastest? Like which ester?
Second.
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 Second. Okay. And why do you think the second is the fastest? See here what is happening. Conjugation is present in both of these. Okay. But what is happening here? You have to also consider one thing, that if you in this methyl, fine, this is having a hydroxy group. Okay. So is some other factor which was possible in this case but not possible in this case, other than resonance I'm talking about? Guys, this group can form a hydrogen bond. Is it possible? In the case of hydroxy alcohols, you will orthohydroxy alcohol, you will find that you can form a intramolecular hydrogen bond here, which will additionally stabilize your positive charge at this position, but which is not possible when your hydroxyl group is present at meta position. So that is why your part B now is going to give you the fastest acid catalyzed hydrolysis rather than C part. So is it clear to all of you why B is giving the fastest acid catalyzed hydrolysis than this C? Any questions, any queries? Am I clear, guys?
Yes, ma'am.
Oh. So if it is clear to all of you, I'm moving to problem number 10. So in problem number 10, you have to identify the major product obtained in the following reaction. So this is the starting material and these are the two conditions, and you have to identify the product of this reaction. So first of all, this amine is treated with chloroform and KOH. So what will happen? This KOH being the strong base. So what will it do? It will abstract the acidic proton. Which is the acidic proton? Your chloroform has this acidic proton. So this will form a CCl3 minus. So this proton is now vanished and you have this CCl3 minus. So again one chlorine will leave out to give you this carbene. Basically here the carbene formation takes place. So can anyone name this reaction? This is a name reaction. The reaction of amine with CHCl3 and KOH. The first step is a name reaction. Can anyone name it? Okay, so let me do this for you. So here amine is reacting with a carbene, that is CCl2. It is a carbylamine test. So basically it is used to identify the primary amines. So if you have to identify primary amine in a mixture of secondary and tertiary, this primary amine is going to give you the carbylamine test. So this is a lab test also. So it is the carbylamine reaction. This first reaction is the carbylamine reaction. So what is happening in this case? So here CHCl3 and KOH react with each other to give rise this carbene. This CCl2, now this amine lone pair will attack on this carbene to give you this species, which after the removal of H plus will get you this, and this nitrogen lone pair now will come down and one of the Cl will knock out to give you this imine. So after the formation of imine, you have this OH minus that is coming from KOH. So this OH minus will, in the presence of base, basically this HCl will liberate to give you isocyanide formation. So isocyanide is going to form from amine in the presence of CH chloroform and potassium hydroxide. So this is a carbylamine reaction which is famous for converting primary amines to isocyanide. So if you have a primary amine in the reaction and you will test it by adding chloroform and KOH, so it will give you the formation of isocyanide. Okay, so this is a name reaction, that is carbylamine reaction. So this is clear that in first step you are ending up having the carbylamine in hand. Now the second step is the palladium carbon and hydrogen. So this is the hydrogenation reaction condition. So what will happen in the case of hydrogenation? So what will happen in the case of hydrogenation, guys? So this N cyanide group will take up one proton. Basically here if you go, these hydrogens are taken by carbon and this nitrogen will stabilize the charge. So basically a complex with NHCH3 is going to form, because here you will have now the triple bond C. So in this case you will end up having a CH3 at this position and NH because of the hydrogenation. So this bond is now become single. And one another thing which is happening in this reaction is this cyanide. Now in the presence of palladium charcoal and hydrogenation, this cyanide is also getting reduced to give you the primary amine. So this is also a thing that in the case of hydrogenation reaction, CN, the cyano group, is reduced to primary amines. So here you will have a reduced function of all these three things, that is the isocyanide, this ketone and this cyanide. So in the first case carbylamine reaction is taking place to generate this isocyanide at this position of amine. In the second step, that hydrogenation is taking place to give you this NHCH3 from coming from the isocyanide. This CN is also getting reduced and this ketone is also getting reduced. So ketone is getting reduced to alcohol, and this cyanide is getting reduced to primary amine. Okay, so now anyone tell me what could be the possible answer now? Which is the correct
Option D.
option D?
Op- Fourth option.
Yeah, option number 4 will be the correct option. Okay, so basically, first is the carbolamine reaction, second is the hydrogenation of all the groups. Okay, reduction of all the groups basically. So now, is it clear to all of you problem number 10?
Yes.
Yes, ma'am.
Okay, so moving to problem number 11. So in problem number 11, they are asking the product from the following reaction. So you have this bromide and they are adding zinc. First, in the first step, they are adding zinc. Can anyone tell me what will zinc do? It is also a name reaction, huh? So can anyone tell me what will zinc do? Zinc being a metal, what it will do? If I take a magnesium in the place of zinc, then what will magnesium do? Tell me, guys, what will happen? You have this Br in the starting material. If I add magnesium in the first step, then what will magnesium do? So what the magnesium being a metal, it will oxidatively insert between this carbon Br bond to form you the Grignard, right? CmGbr. Similarly, based on the similar line, if you have this zinc metal present in the reaction mixture, it will first oxidatively insert between this Cbr bond. Okay, so this Cbr bond now is converted into zinc being inserted and Br, right? So this bond is now converted into this ZnBr. So zinc is oxidatively inserted between this CBr, CX bond. Okay. So after the insertion, now tell me, this is becoming a positive center because of the metal. This is becoming a negative center because of the electron negativity difference, right? So in the second step, they have added aldehyde. So what will happen? Can anyone tell me what will happen if you have added in the second step the aldehyde, and you have a negative, that is a nucleophile in the reaction mixture? Basically, this is a nucleophilic species that is going to generate after the addition of this zinc. So this nucleophile now is going to attack on this aldehyde, right? So what will happen? Now this zinc, first of all, will oxidatively insert between this CBr bond to give you this zinc Br. Then, being a negative charge here, basically what will happen? This ZnBr will get a positive charge. Why? Because of the electronegativity difference between carbon and zinc, carbon is getting a negative charge because zinc being a metal is highly electropositive in nature. So positive charge is there, and negative charge is generated at this position. So now this carbon is becoming nucleophilic, so it will attack onto the aldehyde carbonyl carbon to give you this species. So now you will have a O minus at this position, and zinc Br is becoming the counter anion. And also in the same starting material, you are having another carbonyl group which is present in the form of ester. So this oxyanion will not stop here because of the presence of ester in the same starting material. If this ester is not present, if there is no carbonyl group, no electrophilic center which is present for this nucleophile to get trapped, it will abstract proton from the solvent and become the alcohol. But you have a carbonyl group here, you have the electrophilic center present in the starting material. So that is why this oxyanion now doesn't stop at this stage, and it will again react on this carbonyl compound of ester. And when this oxyanion come down, OET being a good leaving group, it will leave out to give you this molecule, this cyclized molecule. So is it clear to all of you how this cyclized molecule is going to form, the mechanism of each step?
Yes, ma'am.
Okay. So now the option number, which option is correct?
Third.
Third option. Option number third will be the correct one. So here, what is the name of this reaction? Can anyone name this transformation? This is a Reformetsky reaction. Okay. So this is Reformetsky reaction. So this is how, first of all, zinc will coordinatively insert between this CBr bond to generate a nucleophilic center, and then electrophilic trapping will take place. Okay. So now coming to problem number 12. So here they are asking which of the following is the most reactive in dilute aqueous NaOH. So based on the previous things which we have discussed about the ester, acid chloride, amide and anhydride, you have to figure it out which will be most reactive in presence of sodium hydroxide. Sodium hydroxide being a nucleophile, right? So if it is a nucleophile, then tell me which is most reactive towards this nucleophile. Can anyone tell me?
Acid chloride.
Yeah, acid chloride. We have previously discussed, guys, that it is also a nucleophile, and here also nucleophilic substitution is going to take place after the dilute aqueous NaOH reaction, right? So we have discussed that in the nucleophilic substitution reaction, acid chloride is higher in reactivity, then acid anhydride, then ester, and then amide. So here also the similar concept will take place. So here hydroxyl will attack on this acid chloride, and Cl minus will knock out. Right, so it will be most reactive in this dilute NaOH case, because this is also behaving as a nucleophile, and here also substitution is taking place. So similarly, you will have the similar concept and similar reactivity competition between these four. Okay, so is it clear why the acid chloride is the correct answer?
Yes, ma'am.
Okay, so now coming to problem number 13. So in the problem number 13, they are asking the correct decreasing order for acid strength is. So you have to identify the decreasing order of acidic strength. So in all the acids, you have the alpha substituent present, right? In one case you have fluorine, in one case you have nitrile, third case you have nitro, and fourth case you have Cl. So now tell me which is having the higher electron withdrawing ability. The substituent I'm talking about. Fluorine, nitrile, nitro, or chlorine. Higher electron withdrawing ability.
Nitro,
Nitro.
Nitro.
Yeah. After that,
cyanide,
cyanide. After that,
fluorine and chlorine.
yeah. So here, if you see that nitro has the highest electron withdrawing ability, then cyano, then fluorine, and then chlorine. So here you have to answer according to the acidic strength. So now, guys, I have told you higher the stabilization of this carboxylate anion, which is going to form after the dissociation of this acid, higher will be the acidic strength of that acid, because it will now readily give you the H plus ion in the reaction mixture. So if the on dissociation it is going to give you the higher concentration of H plus, then higher dissociation will be there. If higher dissociation will be there, the Ka value increases. Ka value increases, that means the acid acidic strength of that particular acid will increase. So That is why we are saying here that higher the stability of carboxylate ion, higher is the acidic strength. So now tell me which is the correct option, the decreasing order for the acidic strength.
Option 3.
Option 3. Yeah. Yes. So here nitro will stabilize your carboxylate anion very highly. That is why this acid will become strongest acid between these four. Now here nitrile will become the second strong acid, fluorine the third strong, and chlorine will be the least strong acid among these four. Right? Because of the stabilization of COO minus. Negative charge stabilization, and also the negative charge stabilization will take place when higher electron withdrawing electronegative atom is connected at the alpha position of the acid. Okay, so third option will be the correct option. So is it clear to all of you? This is a very simple question. So is it clear?
Yes, ma'am.
Okay.
Yes, ma'am.
So here you can see that nitro, cyanofluorine, and chlorine. So now coming to problem number 14. So in the problem number 14, they are asking among the following acids which have the lowest pKa value. So now you have to answer according to the pKa value. So what is pKa and how it is related to Ka? First you need to know that. So pKa and Ka, I have told you Ka is the dissociation constant for the acid and pKa is the negative log for this Ka. So basically higher is the Ka value and lower is the pKa value. So if higher Ka is there, that means the acid is strong acid. For strong acid, pKa is lower, but Ka is higher. But for weak acid, your Ka value is lower and pKa value is higher, as you can see in the graph. So in this chart, you can see that weak acids have higher pKa value, but Ka value is less. What do you mean by Ka? The dissociation constant value. So is it clear that yeah, here weak acids are having lower dissociation, that is why lower value of Ka and higher value of pKa. But strong acids have higher dissociation ability, that means higher value of Ka but lower value of pKa. Okay. So this is how
Voice is break.
voice is breaking. Okay. So now it am I audible?
Yes, ma'am. Audible.
Okay.
Yes, ma'am.
Okay guys, so what I have told you that how pKa and Ka related to weak acid and strong acid. So I have told you already that Ka is higher for strong acid. What is Ka? The dissociation constant. So higher this is dissociation constant, stronger is the acid. But pK is actually related to Ka by minus log of K. That means higher will be the value of Ka, lower will be the value of pK. Right? So when we come to strong acid and weak acid, you can see here weak acids are having lower dissociation constant. That means pKa value will be higher for weak acids and Ka value will be lower for weak acid. So right. So in the case of strong acid, what is happening? Strong acid have higher dissociation ability. That means it will have a higher Ka value but lower pKa value. Right? So this is how we can relate the K and pKa with strong and weak acids. Fine. So now coming back to the question. So here they are asking among the following acid which have the lowest pKa value. So you have to calculate lowest pKa. Lowest pKa means higher Ka value, right? Higher Ka value means higher dissociation constant. Higher dissociation constant means higher will be the acidity of that particular acid. So you have to basically figure it out among these four, the strongest acid. The strongest acid will have a higher Ka value but lower pKa value, lowest pKa value, right? So which is the strongest acid among these four? Can anyone tell me which is the strongest acid among these four?
For formic acid.
Formic acid. Why formic acid? Because I have told you already the negative charge stabilization you have to look at, right? So in all these cases, the negative charge is stabilized or unstabilized. So here you have the methyl group adjacent to it. So here it will give you the electron towards this oxygen, because methyl is the electron releasing group. So here methyl will do the electron crowding around the oxygen ion. But when you come to the formic acid, you have only hydrogen here. So that is why the electron density at this particular carboxylate is lower as compared to all the three, because all the three are having methyl groups attached, methyl, ethyl, isopropyl. So can anyone tell me which will be having the highest pK? Means which acid will be least acidic? Like you have to tell me the weakest acid amongst four. You have told me the strongest acid, that is formic acid, but now tell me the least like weakest acid among these four.
Third.
Third.
Third one.
Yeah, third. Because now on the same carbon you are having two methyl group, which again destabilize the oxy ion which is forming in this case very much. So third will be the least strong acid, that means the weakest acid, having the higher pKa value, highest pKa value, because Ka value is lowest for this and pKa value is highest for this. So formic acid having the higher Ka value, highest Ka value, having the lowest pKa value. That means, okay. So it is the strong acid having highest Ka and lowest pKa value. So second is the correct answer. So is it clear to all of you the relationship between pKa, Ka, and how it is related to the strong and weak acids? Any questions? Any queries? Okay, so if there is no question, I'm moving forward to problem number 15. In problem number 15, they are asking paracrisol reacts with chloroform in alkaline medium to give the compound A, which adds hydrogen cyanide to form compound B. The latter, on acidic hydrolysis, gives the chiral carboxylic acid. The structure of the carboxylic acid is, now in the sentence form they have told you two conditions. First of all, this paracrisol is reacting with chloroform in alkaline medium. Alkaline medium means basically in KOH or NaOH, basic medium. Okay. So basically you have CHCl3 in presence of KOH in first step, and it is giving you a compound 1, which adds the, in the second step they will add the hydrogen cyanide. Right? They will add hydrogen cyanide to give you compound B. In this reaction, you are getting compound A. This compound A is then treated with HCN to get you compound B. Right? So this is what you have to identify. So here, after the HCN, you are getting the compound B. So now you have to identify the compound B. What is compound B? Fine. So first of all, you need to know what is paracrisol. So this is what the paracrisol look like. So this is paracrisol, basically parahydroxy toluene. This is paracrisol. So now they are telling you that this paracrisol, this toluene, is reacting with chloroform and KOH. So now what will happen? Have you heard about the Raman-Tymon reaction, guys? So in the Raman-Tymon reaction, what will happen? As I have told you previously, in the presence of amine and CHCl3KOH, it will give you the carbalamine test. But if you have this hydroxy group present, basically this phenol, if you have this phenol in the reaction mixture and you treat it with CHCl3, that is chloroform, and in presence of KOH, there is a name reaction which is operative, that is Raman-Tymon reaction. What will happen similarly in this case also, you will have a carbene generation. KOH will abstract a proton from chloroform to give you CCl2. Here, this OH minus, that is KOH, will abstract a proton from chloroform. This again will generate a carbene. So this is dichlorocarbene is getting generated, And now in the reaction mixture you have basic medium, right? So phenol is now present as a alkoxyanion. So here oxyanion is present because of the basic medium. So phenol will come down, this oxyanion will come down, and at the ortho position it is going to attack on this carbene. As you know, carbene is electron deficient species, not the electron rich species, so it is not going to react, it is not going to attack nucleophilic, it is the electrophilic species. So that is why your hydroxy group, that is oxyanion, will come down and it will attack on this carbene to get you this, to get you this compound. So here, first of all, this CHCCl2 minus will take up this proton and form this CHCl3 2. So here hydrogen is going. Basically, there is a shift of this hydrogen from this carbon to this carbon. So here hydrogen is now here, and you have this again aromatized system. So now again this OH minus will attack on this position and will leave out this Cl minus again. So one Cl minus is leaving when KOH is attacking, and another is leaving when this OH will come down. This OH will come down to form the epoxide, form the carbonyl group, and Cl will leave out to give you the aldehyde at the ortho position of hydroxy group. So here, this is a name reaction in which phenol is going to convert into the ortho, uh, is going to convert into the ortho position is going to convert into the aldehyde. So here also similarly, this ortho position of phenol after the Riemann-Diamond reaction is going to convert into the aldehyde. So it is a symmetrical molecule, that is why now here this CHO is now going to attach. So one ortho position is now getting a aldehyde formation due to the first step. So this is the product for first step. This is A basically. So now in another step, what they are adding is hydrogen cyanide. Hydrogen cyanide, now what it will do? As you know, this hydrogen cyanide H is positive, Cn minus. So now it will attack as a nucleophile on this aldehyde. Which is the electrophilic group here? Is it the hydroxy, methyl, or aldehyde? It is the aldehyde only which is behaving as a electrophile. So this is how it is happening. First of all, in the presence of chloroform and KOH, you will have A, that is aldehyde at the ortho position of hydroxy. Now they have added HCN, HCN being the hydrogen cyanide, it will give you the cyanohydrine formation. So basically we have already learned about the cyanohydrine reaction. So this is how it is going to react. So here Cn minus will attack on this aldehyde and generate OH at one end and cyano at one end. So this is basically the cyanohydrine. So again they have told that later, that is compound B on acidic hydrolysis is giving a chiral carboxylic acid. So you have to also hydrolyze this particular B compound to give your answer. So after the hydrolysis, so guys, you previously know that cyano group after hydrolysis will convert into acid. So cyano on reduction is going to convert into the primary amine, whereas cyano on hydrolysis will give you acid. So after hydrolysis, you will generate a chiral carboxylic acid. So how chiral? This carbon is connected to four different groups. That is why we are saying that it is a chiral carboxylic acid. This is the chiral center. So now this will be your product. So is it clear to all of you the series, the sequence of this particular transformation? Any doubts in this? Is it clear, guys?
Yes, ma'am.
Okay. So option number 2 will be the correct one. This option is the correct one. Okay. Because you also have a OH at this position, right? At the ortho position of OH, it is getting activated, aldehyde will be placed. So either 2 or 4 will be the correct one. But in 4, they are missing a hydroxyl group which is forming after the nucleophilic attack at the aldehyde. Okay. So coming to problem number 16. So guys, in problem number 16, you have to find out what is B. So they are giving you a series of reaction and you have to find out this particular compound. So this is again an acid in presence of chlorine, red phosphorus. What it will do? Can anyone tell me what should be A in presence of chlorine and red phosphorus? What it will do? See, basically, guys, the hydrogen which is attached at the alpha position of this acid is very acidic in nature, right? So this will get deprotonate to give you this anion at this position. Because of this acid group here, this hydrogen becoming more acidic in nature, so it will be deprotect very easily. So here deprotonation takes place and anion which is getting generated will attack onto your chlorine, right? So chlorine being this molecule Cl plus and Cl minus. So there is a partial positive charge at one and partial negative charge at one. So this positive charge species is attacked by this anion and this Cl minus will leaves out. So this is what you are going to get. Basically Cl at this position, at the alpha position. So in this first step, you will get Cl at this position, right? So this will become your A. Now the A is treated with alcoholic KOH. So what is KOH? It is base, right? So it is a alcoholic KOH. So now what it will do? Can anyone tell me what will be alcoholic KOH is going to do with A? Any guesses? These are some reactions which you guys have already studied in, I think, 11th or 12th or 10th. So guys, in the presence of alcoholic KOH, someone wants,
Elimination reaction.
yeah, elimination reaction. Here elimination will take place. This base will abstract a alpha proton. So if you have a, instead of acid group, if you have a CH2 CH3 group, then there will be a competition between the elimination which is taking place. Either it would take from this H, either it would take from this H. If instead of this acid there is one CH2 or CH3 group which is present at this position, okay, here you in the molecule you have only one center which is alpha, I mean only one center which is having the alpha hydrogen. But if this acid is CH2COH or is replaced by R, then there is a competition between the elimination, either from this side, either from this side. So then there is a rule which is known as Sedzeff rule, will uh, will actually dominates here and will decides the major and minor product. But from the safer side, in this case, we don't have that situation. So in this case, we don't have that particular situation, and you have only one alpha hydrogen that is present here. So what will happen? This hydrogen will be abstracted by this KOH to generate a O minus, and this O minus again will come here, and this Cl will knock out to give you a alkene formation. So basically, elimination will takes place from this hydrogen and this Cl. So HCl is going to liberate and you will get a alkene formation. So is it clear guys, this question? Any queries? So which option is correct? Option number?
Option C.
Yeah, option number C will be the correct. Fine. So now coming to the last problem of this session, problem number 17. So this is the last question for today's session. So in this question, again, they are giving you a reaction and they are asking this, what is C? What is the last product? Okay, so they are interested in C. So similarly, you have to answer according to the previous question. So this is the acetic acid. You are treating it with lithium aluminum hydride. What is lithium aluminum hydride, guys? I have told you.
Reducing agent.
Yeah,
Reducing agent.
very nice. So it is a reducing agent. So previously also we have discussed, and also we have discussed the mechanism of action of this lithium aluminum hydride. So it is a reducing agent. It will reduce your acid to acid
Aldehyde.
acid to aldehyde, and also again aldehyde to alcohol. It is a very strong reducing agent, guys. So if you see the mechanism in the previous lectures, so for the mechanism you can consult previous lectures. So in that, first of all, the acid is converted into the aldehyde, and again the aldehyde is converted to alcohol. So the last product of the LH reduction is alcohol from acid. Okay, so here in the case of A, you will be having a, instead of acetic acid, now you will have this CH3, CH2,
OH.
OH. So basically you are having ethanol. From acetic acid, you are having ethanol. So now in the next step, they are treating it with pentachlorophosphorus, so PCl5. So now what will PCl5 do? Can anyone tell me? PCl5 will replace, basically this is a substitution.
Chlorine replaced OH group.
Yeah, this is a substitution reaction.
Chlorine replaced the OH group.
Yeah, nice. So here what will happen? This Cl is substituted instead of alcohol. So PCl5, basically from alcohol you will get a chlorinated product. So PCl5 will replace your hydroxyl group. So this is what you will get as B. This is B. Now coming to alcoholic KOH, and you will get the C. Now tell me what will be the answer?
Ethylene. Option A.
Yeah, ethylene will be the answer. So you will get ethylene in the mixture. So this is how you will get. So here acetic acid will give you ethanol in the first step. In the second step, PCl5 reaction will give you Cl, and when you treat it with alcoholic KOH, you will get ethylene or ethene. Okay, so this is how you will get the ethylene. So is it clear, guys? The question, the explanation, everything.
Yes, ma'am.
Okay. So okay, I'm done for today. So this is how you can see the reactions of carboxylic acid and its derivatives. So these are basically the some of the like main reactions which we have discussed today, and I hope this lecture is beneficial to all of you. And I'm closing the session now. So thank you so much, guys, for joining the session. And
Thank you, ma'am.
thank you so
Thank
much.
Thank
you.
you.
Thank you. Bye.
Thank you.